Hello everyone, myself Dr. NCH Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to today's session on Cauchy's integral theorem, verification of problem 1. Now in the last session, I have introduced the Cauchy's integral theorem, and this theorem helps us to evaluate the line integral of the given function of complex variable along a curve C. Now, when we can apply this theorem, if f of z is analytic on and within the closed contour C, if f is analytic at each and every point within the circle and on the circle, then Cauchy's integral theorem states that integral C f of z dz is equal to 0. That means the line integral vanishes, is equal to 0. Now, using this, we can evaluate the line integral of given f of z along the given curve. If this condition holds, that means the function is analytic on and within the circle C or within the curve C, then the answer is 0. Now, there is another model. The function f of z will be given. Now, we need to verify the Cauchy's integral theorem for the given function. That means, we have to show that integral C f of z dz by finding this value equal to 0. Now, verify Cauchy's theorem for the integral z cube taken over the boundary of a rectangle whose vertices are -1 plus 1, 1 plus i, minus 1 plus i. Now here the function f of z is given and the curve C is the rectangle with vertices -1, 1, 1 plus i, minus 1 plus i. Now coming to the solution part, given f of z is z cube. We know that z is x plus iy and dz is dx plus I dy. Next, the curve C is the rectangle with vertices -1, 1, 1 plus i and -1 plus i. Now, if we draw this curve or the rectangle, then we can identify the region or the curve C or the lines along which we need to integrate. So, here first draw this rectangle and here this is the point A, B, C, D and this point is, so here -1, the first one is -1. So, z equal to -1, but what is z? X plus iy. So, x plus iy is -1, that means x equal to -1 and y equal to 0. So, the point is -1 comma 0. So, this is -1 comma 0. The value of y is 0 on x axis. Similarly, the second one, z equal to +1. So, x plus iy equal to 1. So, x equal to 1 and y equal to 0. So, the point is 1 comma 0. Here this is the point 1 comma 0, x is positive and y is 0. Similarly, the other point z is 1 plus I. So, x plus iy is 1 plus I. Now, comparing the real and imaginary parts on both sides, we get x equal to 1 and y equal to 1. So, this is the point C 1 comma 1 and there is another fourth point z equal to -1 plus I. So, x plus iy is equal to -1 plus I. Again, comparing the real and imaginary parts on both sides, we get x equal to -1 and y equal to +1. So, this is the point -1 comma +1. Now, we have to evaluate the line integral along each side of this rectangle. So, therefore, the line integral along C f of z dz is equal to along AB plus along BC plus along CD plus along dA. Now the first one, along the line AB, and here z is the given function is z cube, so z equal to x plus iy, and f of z is z cube, which is x plus iy whole cube. Now along the line AB, we can see here the value of y is 0 on x-axis and x changes from -1 to +1. So therefore, along AB, the value of y is 0 and x changes from -1 to +1. If y is 0, dy will be 0. Therefore, dz is dx plus I dy, which is dx itself, since dy is 0, and x changes from -1 to 1, and since y is 0, f of z will be z cube, which is x plus 0 whole cube, which is x cube, since y is 0. So therefore, the line integral along AB f of z dz is equal to the line integral x cube, and dz is dx, x from -1 to +1. And since this function x cube is an odd function, and using the property -a to a integral -a to a f of x dx is 0, if the function is odd, simply we get 0 here. Or otherwise, if you want, you can calculate x power 4 by 4 from -1 to +1, which is 1 by 4 minus, for lower limit we get -1, and while applying the lower limit again we get -1 by 4. So the answer is 0. Or simply, x cube is an odd function. Therefore, the integral value is 0. So the first line integral along AB is 0. Similarly, we need to find the remaining 3 line integrals. Now coming to the second, along BC. Along BC. So if you draw the curve, you can identify the limits. Here along BC, now there is no change in x value. So x equal to 1, that is fixed, and y changes from 0 to 1. So along BC, x equal to 1 and y changes from 0 to 1. If x equal to 1, dx will be 0, and therefore dz is dx plus I dy. So dz is I into dy, since dx is 0. And what is f of z? Z cube, which is x plus iy whole cube. Here x is 1, 1 plus iy whole cube, which is a plus b whole cube, a cube plus 3a square b plus 3ab square plus b cube. So this is 1 plus 3iy plus 3i square is -1 y square, plus this I cube can be written as I into I square, and I square is -1 y cube. So this is 1 plus 3iy minus 3y square minus iy cube. So this is f of z. Now we need to integrate this. So line integral along BC f of z dz is equal to the line integral, and y changes from 0 to 1. Therefore, the limits are from 0 to 1, and f of z is 1 plus 3iy minus 3y square minus iy cube dy. So if we integrate this expression with respect to y, we can find the line integral along BC. So here the first part on dz is actually I dy. So here we have I. That I comes outside, and integral of 1 is with respect to y is y plus 3i y square by 2 minus 3y cube by 3 minus I y power 4 by 4 from 0 to 1. So by applying the upper limit, here we get 1 plus 3i by 2 here minus 1, y equal to 1. So, minus I by 4. For lower limit, we get 0. And which results as I into this 1 minus 1 gets cancelled. So, 4 LCM, 6I minus I. So, 5I square by 4, which is minus 5 by 4. So, the second result is minus 5 by 4. The line integral along BC is minus 5 by 4. Similarly, we need to find along AB is over, BC is over. Now, along CD and DA left. Now, along CD, you can clearly identify that here x minus 1, 1, here the point 1, comma 1. So, the value of y doesn't change here. So, y equal to 1, that is fixed. Now, the third one, along CD. Along CD, the value of y is 1 and x changes from here, x value is 1 here, whereas here minus 1. So, x changes from 1 to minus 1. 1 to minus 1. Since y equal to 1, dy is 0 and dz is dx plus I dy. So, dz will be dx itself since dy is 0 and f of z is z cube x plus iy whole cube, which is x plus, since y equal to 1, x plus I whole cube. Again a plus b whole cube, a cube plus 3a square b plus 3ab square plus b cube. So, by simplifying this, we get 3x square I square is minus 1. So, minus 3x and here minus I. Since I cube can be written as I square into I square is minus 1. So, we need to integrate this. Therefore, the line integral along CD f of z dz is equal to x changes from 1 to minus 1. We need to integrate this function x cube plus 3x square I minus 3x minus I with respect to x. So, by integrating, we get x power 4 by 4 plus 3x cube by 3I minus 3x square by 2 minus ix from 1 to minus 1. First, the upper limit with negative sign. Here we have even power. So, we get 1 by 4 with minus sign because x cube is here. So, 3 cancel. So, here we get minus I and this is positive power. So, minus 3 by 2 and again plus I since x equal to minus 1. And now, for the lower limit, we get a negative sign. So, first minus 1 by 4 and again here minus I. Already we have negative sign. So, one more negative plus 3 by 2 plus I. Now, minus I plus I plus I minus I plus 1 by 4 minus 1 by 4. So, the result is 0. So, along CD the line integral is 0. Now, the fourth one along DA. Now, along DA, once again go back to the curve. Along DA, here the x value is fixed, x equal to minus 1 and y changes from 1 to 0. X equal to minus 1 and y changes from 1 to 0. If x is minus 1, dx will be 0. Therefore, dz is dx plus I dy, which is, since dx is 0, I dy, dz is I dy. Now, let us find f of z. F of z is z cube. So, z cube x plus iy whole cube, but x is minus 1 here, minus 1 plus iy whole cube. first simplify this, then we will integrate with respect to y. So here a cube, so minus 1 whole cube minus 1 plus 3a square b, so plus 3a square b iy plus 3ab square, since we have minus here, minus 3ab square I square y square plus I cube y cube. So by simplifying this, minus 1 plus 3iy, I square is minus 1, so plus 3y square, I cube is minus I y cube. So therefore, the line integral along dA f of z dz is equal to y from 1 to 0. We need to integrate this function with respect to y. So this is equal to, now integration of a constant that gives the variable itself, so minus y. Yeah, here again dz is I dy, so that I comes here. So I into the first part, minus 1 integral of minus 1 dy is minus y plus 3i y square by 2 plus 3y cube by 3 minus I y power 4 by 4 from 1 to 0. So here the upper limit is 0. Now while applying the lower limit, already we have minus 1 minus sign here. For lower limit we get one more minus sign. So this becomes plus 1. Then minus 3i by 2, and again here minus 1, and here minus, for lower limit again we get minus, plus 1 by 4. So this is, these two gets cancelled. This is I by 4. Okay, this is I into I by 4 minus 3I by 2. So I into 4 LCM I minus 6I. This is I into I minus 6I 5 minus 5I by 4. If you multiply with this I, we get 5 minus 5I square by 4. So which is 5 by 4. Hence, the line integral f of z dz is equal to along AB plus along BC plus along CA, BC, CD and along DA. Now along AB it is 0, along BC minus 5 by 4, along CD 0, along DA plus 5 by 4. So 0 minus 5 by 4 plus 0 plus 5 by 4. So the answer is 0. Hence, the Cauchy's integral theorem is verified, since the integral is 0. So like this we verify the theorem by finding the line integral along the curve. In today's session, we have discussed the procedure of verifying the Cauchy's integral theorem for the given function f of z. So the verification means we need to prove that the line integral of the given function f of z dz along the given curve C is 0. So here we cannot use the theorem, we need to verify the theorem. That means we need to evaluate the line integral along the curve. For example, if the curve is a rectangle, along each line we need to evaluate the curve, evaluate the line integral and then add all the values and show that the final result is 0. So in the next session again we will discuss about the same method. We verify the Cauchy's integral theorem for problem number 2. So this is for today's session. Thank you very much.